Well, the equilibrium extra review. For part A, this balance equation is the best one. And you know that because here's NO2. And, ignore these darker lines that I drew in here. The NO2 was started right here at 0. So because NO2 started at 0 and increased in concentration, therefore it has to be the product. And now on B, starting the reaction with NO2 being 0.08, so NO2 is going to start way up here and it goes down and it ends at the same concentration. The N2O4 starts at 0 and ends at the same concentration it was, because the concentration ratios have to remain the same for NO2 and N2O4. That's the equilibrium constant. So that's how that goes. With question 2, hopefully you got 0.035 for that. Basically what you do, this is the reaction that we want right here, and this is the reaction that we have, and the equilibrium constant is 794. So first of all, notice that HI is on the left-hand side, and so we switched this reaction right here. We reversed it. When you reverse it, you take 794 and raise it to the -1 power. Okay. Then you cut the reaction in half. There's half H2, half I2, and only one HI instead of 2. So after you take the inverse, then they cut the reaction in half, and then you want to square root it, and you get 0.035. With question 3, 0.018 is what you should have. The numbers are all given to you. The equilibrium constant Kp is the pressure of H times the pressure of I2 divided by the pressure of Hi squared. So the pressure of H2 and I2 are right here. So put that in the numerator, 0.708. That goes in the product, or I'm sorry, in the denominator, and it's squared because of the coefficient there. 0.018 is what you should get. Number 4, why is this heterogeneous? Well, it's heterogeneous because not all the states are the same. You've got two gases right here, and you have a solid right there. That's a heterogeneous equilibrium. If they're all gases, then it is homogeneous. Or if they're all aqueous, it's homogeneous. If there's a mixture, then it's not. Now remember, when it's heterogeneous, pure solids like this, or pure liquids, are not included in the equilibrium constant expression. So down here in part B, Kp equals pressure of NH3 times the pressure of H2S. There is no dividing by NH4HS because it's a solid. It does not appear in the problem. So 0.07 is given to us right there. It's the equilibrium constant. And we need to find out the basically just find out X. Okay, calculate the equilibrium partial pressure of ammonia. Well, the partial pressure of ammonia is going to be X, and the partial pressure of H2S is also X. So here's our setup. 0.07 equals X times X, and you just solve that equation. X turns out to be 0.26. Now the value of Kc, what I got is 1.19 times 10 to the -4, and you plug in the given 0.07. Kc is our unknown. The change in the moles of gas is 2 because it goes from 0 and goes to 2 moles of gas. So 2 it is. All right. Now the back page, we've got pressure of O2 is 17.9, and there's the setup for it. 36.1 minus 2x, x and x. So you're going to have x squared over this squared as well. So here's what I've got. Take the square root of both sides. There's the equilibrium constant that's given in the question. Take the square root of both sides, just solve for x, and we see x equals 17.9, and that is, x is the pressure of the O2. Now 6, if Kc is very large, what does that tell us about the concentration? There are lots of products. Because Kc is products over reactants, if it's a big number, then the products have to be a big number in the numerator. And number 7, more reactants are going to form. If Q is greater than K, that means Q is too big. The numerator is too big. And so the products have to decrease, the reactants have to increase. Here's what we got for 8. Dividing everything, all the moles, divide them all by 5. You got 5-liter container here. And so I did that right up here. And here's my ice diagram, 0.15, 0.13. These guys start at 0. And the final is 0.06. That was 0.3 divided by 5. So that's the equilibrium concentration. These guys are going to both be the same. 0 plus 2x is 0.06, so this is 0.03. X equals 0.03. Plug that in. 0.13 minus 3 times 0.03 is 0.04. And similarly here. Then you've got equilibrium concentrations. Plug it in. Products over reactants. So these guys get squared. Cube the oxygen. Square the H2S. Number 9, you should have 1.02. If you got 25 for 8, you just plug it into this equation right here. The change in the moles is -1. Delta N is -1 because here up in the balanced equation you got 5 moles total, decreasing to 4. So you get a Kp value of 1.02. Kp is going to get larger here if the size of the container decreases, so the pressure increases. If you decrease the container, the pressure is going to get larger. And the pressure getting larger, you've got Kp is going to be products over reactants. If the pressure gets larger, the reaction is going to want to reduce the pressure. Let's look at the balanced equation again. The reaction is going to want to shift to the product side. Look, there's only 4 moles of gas over here, 2 and 2. Here, there's 3 and 2. So the 5 moles of gas would rather be 2 moles. If the pressure increases, that will help it to become 4 moles. That'll help it to become, to lower the pressure. And if these guys increase, then the equilibrium constant gets larger. Okay? Now, if the temperature is increased, now right up here it says it is exothermic. That means that the heat term is a product. So we can even do plus heat. If you raise the temperature, the reaction will shift away from the heat and go make more reactants and fewer products. Products get smaller, reactants get bigger, and your equilibrium constant therefore gets smaller because the reactants are on the bottom and they're getting bigger, so the denominator is larger. Finally, with 12, well, almost finally, I divided all the moles by 2.5 in the problem because we have a 2.5 liter container. There's my ice diagram and my value for X. And plugging in the equilibrium concentrations, I got 51.5. Last one, number 13. Here's my, well, sort of an ice diagram. I was running out of room. I got 0.02 minus X, 0.02 minus X, X and X. And where did 0.02 come from? Well, there's 1 mole in a 50-liter container. Okay. And so X times X divided by this and this looks like this. X squared over 0.02x, 0.02 minus X squared is 0.58. 0.58 is the given equilibrium constant. Take the square root of both sides. I got this. Then I solve for X. X was 0.00865. That is the concentration of CO2 and H2. And then I just took 0.02 minus X, and I got 0.01135. That's the concentration of CO and H2O. So there you have it.